Hello everyone, April 14th. Alright, let's do this. I did this one already. That's yesterday. No, we're gonna have to do this maximum value of k coins from pile. There are n piles of coins on a table. Each pile consists of a positive number of coins of assorted denominations. In one move, you can choose any coin on top of any pile, remove it, and add it to your wallet. Given the list of piles, where pile I is a list of integers denoting the composition of the ith pile from top to bottom, and the positive integer k return the maximum total value of coins you can have in your wallet if you choose exactly k coins optimally. Okay, so the first example, we have two piles. The first pile has 103. Second pile has 789. And we're asking k equals to 2. What is the best strategy we can get? Well, the answer is 101. We can choose the top. And then the second will be, 7 coins. N equals smaller equal to 1,000. And we already know what the solution will look like. It's going to be DP. I think we are in the DP week, whatever that means, right? Okay, so what's the state, right? So for solving DP problems, always trying to find the state first. Like, how can we represent the state? Well, we have piles, n piles, right? N piles, okay? And n piles, and we can take anything from the n piles. And we want to take k. So it has to be k, has to be one of the state. Like at, let's say jth, if you take the jth coin, what's the maximum at jth coin? And then you can want to take the j plus 1s, and you can go through all of them and try to find one of them. But 1,000. Because the pile, how about each pile? The length of each pile. Well, that doesn't matter, the length of each pile. Well, actually it does. What if we exhaust a pile? It never said, right? It never said. I know pile length is so I have n piles. And piles, that's ij, that's the thing. K smaller is 2,000, right? So the pile's length, sum of the pile's length is 2,000. So it seems like should be m and k, right? Think about it. In the final solution, what do we have? Well, we have some sum. So maybe we can do like a prefix sum, right? A prefix sum for each pile. And then the result will just be some index on the first pile, some index on the second pile, all the way to the end. And then we want that sum to be maximum. And then the total number. Okay. So let's say we have k minus 1. We take k minus 1 coins already. Right? If we take k minus 1. Hold a second. Now, if we take k minus 1 already, now we want to take the kth right? But the previous k minus 1 can have different ways of taking. Are you sure it's going to be the maximum? Well, ideally, the case I can take anything that's currently available, right? And then whatever the previous max, and we'll do exactly k. Exactly k. So we'll take k coins. K coins. I'm drifting towards binary search again. I'm thinking, if you can, the maximum you can take is k coins. If the the size of the pile is larger than k, then the maximum you can take from a pile is just k, right? So what if we get everybody out, sorted them? We sort it, and every value is a prefix sum. Okay, every value is a prefix sum, so we sorted it. And what would you want to do? Well, you want to go from the maximum, right? And there are many choices. There are different choices. Because they can add together, and then it might be a bigger value, right? So let's say we have take 1, and then take 2, and take 3. Okay, take 1, we have these values. Take 2, we have these, and take 3, we have these. And everybody is also have the index. Okay, and then what? And then we should try and take k. So if you want to take k, you can take k from one pile. Then you have your maximum. Okay, and you can say, okay, how about I take k not from one pile, from 2 piles. Well, from 2 piles, then it has to be a k minus 1. You want to find a maximum k minus 1 and a maximum of 1. And what if they overlap? Well, if they overlap, then we can do maximum of this with the second largest, and the maximum of this with second largest of that. So what's this? What have we converted this problem to? I'm gonna say 3 piles. Okay, we'll do 3 piles, and then we can say, but that's we have a lot of options then. 3 piles. No, I don't feel like it. I don't feel like it. And binary search doesn't feel like it either. But if we do DP, again, we need a state of each thing. What type of state can we do? Index, right? We can do index. Okay, let's think about index. Piles, index. So I can say from the ith pile to the end, right? Like on the current pile, I say I take 1, and then right? I want the maximum in the remaining. Maximum in the remaining. None of them is taken. So from I plus 1's pile to the end, what is the maximum we can get? Or I take 2 in the front, and what's the maximum we can get? So what we're saying is we start taking from the ice pile, right? From the ice pile, and with, you can say, P, number of coin left, okay? With P number of coin left. And we can take 1, we can take 2, we can take all of them. That might work. I don't know. Wait, 23. Still. All right. I'll give this a shot. I'm not sure. Very unsure. So, func tools. Okay. So let's say DP, right? It's from index and then remaining, right? Remaining, and then we'll return the maximum thing. And n equals to len piles. So of course, if index is larger equal to n, that shall return return 0, right? It cannot be larger or equal to n. And how about the remaining, right? If remaining equal to 0, right? Then we say if this or remaining is equal to 0, then we have no remain, so we return 0. Otherwise, we can say, okay, we want to find from this index piles to the end with ren number of coins left. What's the maximum we can get? Now, what we can do is for I, do we even need to use I? Yes, we do. For I, let's say coin C in piles index enumerate. All right. Then we can say, rest equal to 0. All right. So we can say we can take nothing, right? We can take nothing. So this shall be dp index plus 1 rem, right? We just take nothing from the current pile. Or we can say we take 1 coin from the current pile, which means in this case s equal to 0. Okay, s plus equal to c, right? And then we say rest shall equal to c. We take this and dp index plus 1, right? Remaining minus I minus 1, right? That's taking 1 coin, and then we do the rest, right? But actually, it's going to be maximum rest and this, and I'll go back up. We're taking 2, right? We're taking 2, or we're taking 3, and once we're done, we'll return rest, and we'll do return dp. So we from 0 with k remaining. So what is the result? Okay, give this a shot. 101. Seven 706. Okay, this is gonna be piles. Okay. Max value. This is piles. Okay. Try it. That was very much not right. smaller equal to. What went wrong? Well, what went wrong? Why would be 1300? That doesn't make any sense. K is 7. K is 7, man. K is 7. Oh, for one thing, that's not C. That's S. That's even more wrong. Piles index. Okay, I see. We'll take this, and then the remaining, we say the maximal, the remaining index plus 1. Remaining minus I minus 1. That seems okay to me. And if index is larger equal to n, or remaining is smaller equal to 0, then we shall return 0. Oh, return 0. That, my friend, is not right. I see that. Because you do s plus, that's why it's not right. Okay, so do we keep this one here? And how do we handle this? We'll do max remaining equals to this. Okay, if max remaining has to be, say, it's larger than 0, right? Then we do max remaining. That is ridiculous. No, it's... Oh, hold up. Now this condition has to be right. Okay, I'll still do this, which is fine, but remaining, I'll handle this remaining differently. I'll get it. I would say if remaining minus I, right, minus 1 is larger than 0, then we will do this, which means there's always something, right? Else, then we just break, because we don't have any more to give, right? How about this? What the? Oh God. That's very weird. All right, now we have to really take a closer look. This is larger or equal to 0, right? Then we say we have this remaining, then we can keep going. If it's smaller than 0, that means we cannot take it anymore, right? That's why we break. Maybe something with this. Well, this is fine, right? This is fine. It should be fine. And this is just accumulate. Hold up. All right, let's run this. Right, we have 7 remaining. Okay, and let's print index remaining and rest. Okay, so we do 0k, right? K is 2. 0, 2 comes in, okay? And then I do 1, 2. 1, 2. And a 1, 2 I do again is going to be 2, 2, but 2 is larger or equal to n, so it turns 0. So 1, 2. We add 1, 2, rest is 0. Okay, so I here, and I'll do this, right? And s plus equal to, so 7, we have 7. And we try, oh, it broke out. You shouldn't break out. Because if this can now do, right, shall be able to keep moving on, right? So it can do like 7, 8. Like there's 7, but then we have nothing, so yeah. But then next one, the remaining is 1, right? But the next one is equal to 0. It should be this, equal to 0. So I shall do this, or rem is equal to 0. That. So we do break out early, but we also, so we handle this. So the only difference, what's the only difference? The difference is we don't keep this running. Yeah, if we keep this running, then s will just get bigger and bigger and bigger, which is not right. Okay. So this one, now it looks promising. Now it looks very promising. Yeah, I'll change this a little bit. If minus I minus 1 is smaller than 0, that would break. All right, we can say no more coin to take. Otherwise, we do this, and then we do this. So save a few lines. Okay, and then we can say S0. Nah, I don't like this. These two are different ideas. Accumulate, right? Accumulate the coin values in the current pile. Okay. You wanna try? Yeah, why not? Well, this one's correct, we know. So what else do we try? 1. I'll take 1. It's kind of the edge case. Try it. Oh my god, I've done it before. I completely did not remember it. Oh shoot! I forgot to LRU cache. Darn. My bad. Forgot. Forgot area cache. There we go. So it's almost 1 year, exactly 1 year ago. I think I did this on my own. It's not part of the challenge. I think that is the solution, the DP solution. We can see what method I used last time. And I forgot to rate it. That's why I forgot I'd done it before. 2218. Use DP. Where DPI J is the max value of coins, max value of J coins taken from piles I to the n. That's it. O NK. Right, ONK. Okay, solution. This is bottom up. Bottom up. That's actually not bad. This is top down. Oh, also bottom up. Oh, go right to left. Oh, you can go from right to left. DPI, which is or PS J plus minus 1, which is the S here, plus DPI minus J. I minus J. The remaining. DP is okay. I don't have any gana to look into this. It's fine. Bottom up. Top down. Yeah, always top down. This type of thing, top down, I think is easier to do. At least for me. Top down is easier for me to understand. Oh yeah, that's actually not true. That's not NK. It's K times S is the total number. Why? Because you have index, right? That's N, right? This is N, K, but within you have to also go through this, right? So it's S. Should say where S is the total number of coins in piles. Yeah, that's more right. That's more accurate. I don't like knapsack. Okay, yeah, that will be it. I'm not gonna keep reading the bottom up. Let's go into new territory. Minimum operations. To reduce integer to 0, you're given a positive integer n. You can do the following operation any number of times. Add or subtract a power of 2. Jesus. Return the minimum number of operations to make n equal to 0. Number x power of 2. If x is equal to 2 to the I, where I equal to 0. Okay, so in the first one, or you can just say the minimum number of power of 2's to add up to this value. Wait. Seriously? Isn't that just binary it? You should just take binary value of this, right? Take the binary and then count how many ones are there. Okay, I'm not 100% sure, but we can definitely try. Right, we can say binary 39, right? We have 4. Oh, geez, we have 4. 1, 2, 3, 4, but it says 3. Dude. Huh? Oh, add or subtract. This is completely subtract. Jeez. Okay, so what do we do? I mean, 40 has 2, right? So we can, I have a 41. 41 has 3. So, because you have to add. Oh, dear Lord. You can add or subtract. Which just means you're given a binary value you want to, because add is an operation, right? And after add, you want to remove as many ones as possible, because then you just count the number of ones, right? Therefore, if you add a 1, if you don't add, right, that's the base condition, you don't add a 1, then you get whatever you have. And then we say we add a 1, 1, right? You add a 1 in here, you can add a 1 in here, add a 1 in here, you can add 1 at each position, and you see how much it goes, and you add 1 at 2 positions, at 3 positions, but there will be combinations. Combinations. But if you want to go greedy, is it greedy? If you have a consecutive ones, it's always better to add at, I mean, we can actually analyze it, right? If we have 1, 1, right? Then if you add a 1, it becomes 1, 0. So you are increasing, right? You're not decreasing the number of steps. If you have 2 ones, you add a 1, and you turn 2 ones into 1, 1, right? So you remove 2, or you add 1 and remove 1. So that's the same. So you might as well not do it. So the only time that it will be beneficial is you have 3 or more. If you see 3 or more consecutive ones, you want to add a 1, right? Because when you do so, you turn 3 into 1, and you remove 1. So the total is 2. So you can save 1. Therefore, we shall analyze the thing. Let's say 54. I don't know what 54 is. Let's just say 54. Okay, that's 54, right? If we do it by itself, it's going to be 4, right? If we do, oh, holy crap, you add a 1, 1, and you can create 3 ones. Holy crap. That, I did not see this pattern coming up. So now that's actually more interesting. This is an interesting pattern, which means if you have ones, right? You have ones that's separate by 1, 0, like 101. If you do 101, you add a 1 at the end, then you get a 1, 1, 0, right? Then you add another 1, you get a 1, 0, 0, 0. So in total, you will do 1 operation, 2 operation, 3 operation. But the original is 2 operation. So that's actually a waste. But if you have 1, 0, 1, 1, I mean, if I have like 2 zeros separating, and I think that's not going to work. If you have 2 zeros separating, then you cannot connect with the previous one, then it's definitely we have to go 3 or more. So if this, right, you have 1, 0, 1, 1. Yeah, that's the thing. If you have 3, we definitely do it. But the case is if we have 2. Now we know if we have 1, don't do it, because it's not worth it. Actually, no. What if we have like 1, 1, 1, 1, 1, 0, 1? I mean, you do a 1, you add 1, and you get a 1. You have to add 2 ones. The analysis. Okay, get back down to basics. Okay, the basics is if we have 1 separated by 2 zeros, right? We can call those our islands of 1, right? Separated by 2 zeros or more. And then we shall treat it as, if it's 1, 1 or 2, 1, we just give it up. Don't even think about it. If it's 3 or more, then we definitely do it. And if we find 3 or more, then the total number will be add 1 and add 1. 2. Yeah, 2. Any of those are 2. Like if we have 100 ones consecutive, right? And the operation is add 1 and minus 1. Done. So 2 operations. That's if we have an island of consecutive ones. Now, the trouble is if we have 2 sets of consecutive ones separated by a single 0. That is a very interesting situation. And we can have multiple ways to analyze it, right? Okay, let's say we have m ones on one side and a 0, and n one on the other side. Okay, so if we add a 1 on the right side, the rightmost side, and then we'll be here, right? Then I add another 1 to this side, right? And then we have 1. So it will be 3 operations. It will take 3 operations if we have this. 3 operations if I have a 0 in the middle. Okay, 3 operations, which means if the original shape has fewer than 3, then we don't use this. Like 101, we don't use this. But if it's 1101, we use it, right? Because it takes 1, 2, and then 3. It takes 3. No matter how you do it, it's going to take 3. 1, 2, 3. Therefore, we need to analyze the binary shape. And how do we analyze it? Now we know, right? We know how it's going to go. So we can just read from, I don't know, left to right to left, doesn't really matter. So we just read, okay? Oh, what if we have a shape of bunch of 1 and a 0, bunch of 1 and a 0, bunch of 1? Then you need to add a 1, like 1 0 1 0 1. How do you do that? Well, every 1 needs to be add a 1. So we'll take 1, 2, right, and 3. That will be 3. Oh, are we saying it's always going to be? Interesting. Hold on. If we have just, let's say 0 and a bunch of 1 again. Okay. So we'll take 1, 2, 3, 4. We'll always take 4, right? So if we have this shape, there's something 0, something 0, something 0, right? We have this kind of pile. We need to know how many number of piles there are, and the result is always the pile plus 1, right? That's going to be. And every time we hit a double 0, then we just stop. So, okay, we read from left to right. Okay, we read from left to right, and then we just read 1 1 1 1 1, some 1, and then we have a 0. And if we have double 0, whatever we have previously, we handle it. And the way to handle it is, if it's 2, if it's 1 1, it's going to be 1. If I have 2 ones, it's going to be 2. If it's 3 or more, then it's going to be 2, because we add 1 and remove 1, which means if it's larger or equal to 2 consecutive, it's going to be 2. If it's 1, it's going to be 1. All right, that's that. Now, if we have a 0, all right, and then we run another consecutive, and we have a 0. We run a consecutive, and we have a 0. All right, we just keep this one going on. Then, before we end, we need to compute the total number of ones inside, okay? Because we know the total operations we need to take, which is the total number of piles, okay? Total number of piles minus 1. And if the total number of ones is smaller than that, then we take the total number of ones. Otherwise, we take that. Okay, so how do we find? We can use group by. Group by. I think that's Zeta Tools. Yes. Okay, let's say, I forgot, for kg in group by binary 54, 2 to the end, print k len list g, if I remember right. That is correct. See, we have 2 ones, 1 0, 2 ones, 1 0, and an end, right? Now we just keep this going, and then we know the total number of piles is 2, right? And the total number of ones is 4. So 2 will give us 3, and then there's 4, so we can return 3. Okay, we can try this. Honestly, this is actually not the easiest medium level, but that's actually quite interesting. Okay, well, I mean, I'm not sure if group by, right? I'm not sure if this is correct. Okay, so what do we do? So we need to say num piles, right? And num ones, right? Num ones. We start with this, and then we say for kg, right, in enumerate binary n 2 to the end. If k is equal to 1, num piles plus equal 1, and num ones plus equal to len list g. Else, that's a 0, right? Else, then we say elif len list g, right? Len list g, that's a 0. How many 0 do we have? If we have 1 0, we just ignore, we keep building. But if this is larger than 1, we have more than 1, then the chain will stop. Okay, then we have the result for rest equal to 0. Now we have to see how many piles. Okay, we say if num piles, we have only 1 pile. Okay, if we only have 1 pile, then rest shall plus equal to the minimum of num ones and 2. Else, num of piles is larger than 1, right? Piles is larger than 1. Then rest shall plus equal to minimum num ones, num piles plus 1. If a 2 pile, we have to go 1, 2, 3 times, right? Num piles plus 1. And after we've done this, num piles equal to num ones will all reset to 0. And we'll return 0, return result. Okay, let's take a crack at this. Actually, you can write it directly. 39, 3. 54, 3. Yeah, both are 3. N. Minimum operations N. You gotta be kidding me. What? Oh, Lord. Oh, okay. What the hell, man? K. Maybe, because maybe if I consumed it already. That doesn't. Anyway, just take a look. What I'm gonna take a look at here. All right, we can say print. I don't even know what am I looking at. honestly. I don't know k. I know what k is. What else? Num piles, num ones. Do we have anything? It does not. Oh, enumerate. What the hell are you doing, man? Where's group by? Wait, enumerate? What the hell? That's group by. Oh, it's still not right, but yeah, it should be group by. Let's do this. I'm just gonna make sure that if s. Okay, that's not the issue. We can just see print k and s, right? 1 1. If it's a 1, then 1s. Okay. Next is 0 as a 2, so we know it's s larger than 1. Yeah, and hold a second. Where is my thing? Yeah. Rest plus equal 1. That is correct. Oh, I did not consider when it drops out. Dude. Okay, when it drops out, what do we need to do? We have to run this one more when it comes out, right? The last one. If the end is 0, then we would have handled it. If the end is a 1, we only have 1 0, then, or if we end is 1, so we come out and we have to handle, right? Unless the last one is 2 and we handled. If last is 1, interesting. If the last one, then we'll handle it, right? So we need to say if num piles, right? If we have num piles, doesn't really matter, and num's 1, then we shall do this one more time. And num ones, right? Should do this one more time. There we go. It looks ugly. It looks absolutely ugly. Is there a way we can make it look nicer? I'm not sure. I mean, we can do this. We can say if this is equal to 1, then we do this. And then we say elif piles is larger than 0. Then we do this. Yep, we just forgot to handle it at the end. Oh, I like the test case for this. It will be easy to give test cases. 10 to the 5th. I like. Why you have a y there? Now why do you repeat it? Beautiful test cases. N has to, wait, what? I have a too large an n. Oh Jesus. 10 to the 5th. What? Which one? 10 to the 5th. Oh, these are all too big. Any more? That should be good. I think this one might be right. Yup. Good. It took a while, huh? Pure analysis, right? So first of all, if we have an isolated, first of all, turn n, right? Turn n into binary form. If we have an isolated consecutive ones, where isolated means that there are at least 2 zeros flanking, right, the ones, then the minimum moves to remove all the ones is either 1 if there is only one, or 2 if there are more than one ones. We arrive at 2 because we can always add 1 to the last position, which will cancel out all the ones and produce an additional, right? And produce an additional at the front. Thus, the minimum to moves to remove is 2. If we have consecutive ones separated by a single 0, then the minimum moves can either be, right, the total number of ones or total number of piles of ones plus 1. This is because we can always add 1 to the last one of the last pile, and the newly created one can attach to the previous pile, right? And we can perform the same operation again. This results in the total number of moves to be the number of piles plus 1. I use group by to obtain the size of each pile of zeros or ones and analyze from there. ON. The runtime is actually alright, 34 milliseconds. Okay, is there any better solution? Jeez, you gotta be kidding me. You gotta be kidding me. Oh. What? What the hell is this, man? Okay. Uh-huh. Yep. Oh, that's also correct. Wait. Hold on. hold on. If it's a single one, yeah. If a multiple ones, plus 2. But what if I have 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1? It will have 2, 2, 2. How do you handle that? If n is 1, I right shift. What? If n is 1, I right shift to 1. Right shift. No. If n is 0, I right shift to 1. Oh, yeah. If n is 0, shift. And then I will end 2. It's 1, 0. And 2. Is larger than 1. How n2 is larger than 1? 2 is 1, 0, right? So just n is 1. Then n plus equal 1. So it's a 0, 1. Oh, 1, 1. Just something 1. What if it's a 1, 1? 1, 1. No. It's larger than 0. So it has to be 1 something. Right? It has to be 1 something. If it's 1 something, because it cannot be 1, 1. 1, 1. Yeah, we can be 1, 1. It cannot be 0, 1. So the only time is if it's a 0, 1. If it ends at 0, 1, then we will remove that and shift 2. If it's anything other than 0, 1, like if it's a 0, 0, if it's a 0, 0, 0, 0 will be handled by the first one. So 1, 1, right? So 0, 0 and a 1, 0 is handled by the first one. Now we only have 1, 1 and a 0, 1 to consider. If it's 1, 1, then we will basically add 1, result plus equal 1, and then we will keep shifting. Oh, I see how it's done. Yeah. Well, it's easier than yours. Well, same idea, but better implementation. Yep, I agree. It's better implementation. Log n. Oh yeah, that's not n. It's the number of this. Yeah, it's log n. Come on, man. Okay, let's see if you can do it by yourself. Same idea, but better implementation from Lee 215. All right, press 0 and say while n is larger than 0. Okay. Then we say if the last is 0. If n2 is equal to 0. and left shift go to 1. Right, just get rid of any trailing zeros. Elif n and 2 is, well, n and 2. N ends with 1 1, right? And plus equal 1, rest plus equal 1. Always add 1. Else n ends with 0 1. Remove that 1 by itself. Rest plus equal 1, right? And then n left shift 2, and then return rest. Oh shoot. Got it wrong. Right shift, it's not left shift. Alright, so what is this one-liner? Transform multiple ones. Integer sequence. Case of single one, n times 2, n times 3, n to the power of n times 3. Case of multiple ones, single 0 in the middle. Yo, what the hell? What the hell is this? This is some magic. Huh? This is some magic. What? How do you know? How do you know? Oh Lord. N times 2 times 3 and then to the power. Like how? And what does this one even say? I don't even understand what is it trying to say. That's not to the power, man. That's exclusive OR. Jeez. Exclusive OR n and 3 times n. So what does this compute? Optimal cost function between two processors at distance n. Huh? This comment does not help at all. Like, what does processors mean? I mean, we can see this is what we want, right? This one is what we want. But that's in Haskell. It doesn't matter. This is what we want. But what does it mean? Right? What does this thing mean? This is just papers. Comment doesn't make any sense. Oh, is this the? Is 1, 2, 3, 4, 5, 6, 7. Ah, this is the sequence. This is the sequence. Ah, optimal cost function between two processors at distance n. Doesn't matter, this is the one. Holy crap. N times 3. I don't know why you have to add n times 2. But n times 3. And the exclusive OR. Dude. Yeah, you missed something. It's just a magic trick. All right, we can read this. All right, I'll oblige. I don't like this one. Screw you. Well, the you might want to find a platform where latex can be displayed. It's really a pain reading it this way. But I mean, you know what? Are you interested in this? Do you want to know? Honestly, I don't. I don't want to know. I do not want to know, but well, we'll see. we'll see. All right. Anyway, we are past today's, so we're gonna end right here. But man, this solution 3 is lordy. Is it really lordy? Magic solution. The proof allegedly is here. I think I spelled it wrong, but it's okay. But I haven't gone through it yet. Return n exclusive or n times 3 and binary of this count 1. I'll leave it here. Maybe I'll get interested. Who knows? A good question though. That's actually not, it's actually not as fast. I thought it would be like super duper fast. Okay, I will see you guys tomorrow, and I'll read this in overleaf. Adios.